Thank you. Yeah. Okay, so it seems we're asking ourselves today, what is computation? And either does nature compute, or how does nature compute? And there's an amazing fact that motivates both those questions. And indeed, it motivates every other foundational question about computation as well. It is this. Take any physical variable whatsoever, like, for example, who's going to be the next president of the United States, to take a topical example. Or another one is the mean temperature of the Earth's atmosphere as a function of time. And ask exactly how that variable depends on other variables. Then the answer will always, invariably, be a computable function. Or, if there's quantum indeterminacy involved, then the probability distribution function will be a computable function. This is because the laws of physics refer only to computable functions, or again, either directly or via computable differential equations. Now, the reason this is amazing is that most mathematical functions are not computable. In fact, the set of computable functions is of measure 0 in the class of all mathematical functions, let alone in the class of all mathematical relationships. So there is something infinitely special about the laws of physics as we actually find them, something exceptionally tractable, prediction-friendly, and computation-friendly. That's clearly not accidental. So there's definitely something there to be explained. But what people make of it depends on, people make different things of it, and what they make of it depends on quite deep aspects of their worldview. Of course, religious people tend to see divine providence in it. And some evolutionists see the signature of evolution, namely apparent design, but at the level of laws of nature, to make them computable. And cosmologists see anthropic selection effects, and computer programmer type people, well, they see either a great computer in the sky, in which we're all simulations like in the movie The Matrix, or that the universe itself is a computer. And either way, that what we perceive as physical phenomena are actually just virtual reality, running programs. Now, all those conceptions are wrong because they all share a fatal flaw. Now, they all have other flaws as well, but I want to concentrate on the shared one, which is relevant to our question, what is computation? The laws of nature are, by definition, inviolable. For instance, you can't make a perpetual motion machine. I hope you're seeing the slide now. On the way here today, I saw a headline on the BBC that said, "The future of physics is in jeopardy." But that's exactly what can't happen. The future of physics is unchanging, inviolable, invariable. It's only what we do that can change. So there's something inviolable in the universal truths of physical laws. And also, the theorems of mathematics are inviolable. For instance, you can't change which of two integers is the larger. So in both cases, inviolable refers to a fact of the matter, meaning it can't be argued away just by changing terms or definitions. For instance, you could define the term perpetual motion so that a glass of tap water is a perpetual motion machine because the molecules are literally in perpetual motion. Nevertheless, that wouldn't enable you to use that motion to charge up batteries in a cycle. That's a fact of the matter. And similarly, in arithmetic, you can redefine the word billion, which in British English used to mean 10 to the 12, and was then redefined down to 10 to the 9 in line with American usage. But that renaming doesn't make any actual number bigger or smaller. That's another fact of the matter, but of a different kind. So the laws of physics and the truths of mathematics are equally inviolable. They are universal truths, and they're both about something objective. So they're alike in those respects, but nevertheless, there's a well-recognized important difference between scientific and mathematical truths. It is in what these fields are about. Mathematics is about absolutely necessary truth. Such truths are all abstract, and essentially they're truths about what is or isn't logically implied by particular axioms. But science isn't about what's implied by anything. It's about what is really out there in the physical world. Laws of nature do therefore have to be consistent, but unlike mathematical axioms, they also have to correspond to reality. So that's the fundamental difference between mathematics and science, between theories and theorems. Now, what about the laws of computation? By a law of computation, I mean any inviolable generalization, any universal truth about computation, such as that there exists no computer that can reliably detect whether a program will eventually halt or not, or whether it'll do any given thing. And in order to understand what computation is, the most basic question we have to address first is, into which of those two categories do the laws, the inviolable laws of computation, fall? Are they absolutely necessary truths, or are they determined by the laws of physics? Now, the answer is they're determined by the laws of physics. But there's been a lot of confusion in regard to that. And to explain what's going on, I have to look at this in a slightly broader context. The context here is that the theory of computation, which is a branch of physics, was pioneered by mathematicians. Now, that's not unusual. Several other important branches of theoretical physics were also started by mathematicians, for instance, geometry and probability theory, and various theories involving the infinite and the infinitesimal, calculus. And indeed, in many of those cases, this same confusion that I'm going to describe here did arise. In terms of this distinction between reality and necessary truth, the confusion keeps arising because mathematicians tend not to have a very firm grip on reality. Here's what happens. Take a mathematical idea, say the idea of infinity. And mathematicians realized centuries ago that they really can work with infinity. They can elegantly define, say, what an infinite set is, as one that can be placed in 1-1 correspondence with a proper subset of itself. And then they can prove theorems about such sets and about further abstract structures if they can consistently define them in terms of such infinite sets. And sometimes they can then use those mathematical structures and theorems to formulate new scientific theories or to make existing theories more precise. For instance, as calculus was used by Newton and Leibniz to formulate theories, scientific theories, about things like instantaneous velocity and other rates of change. Okay, so far so good. But notice that the concept of instantaneous velocity in physics and in common sense doesn't involve anything infinite. And indeed, nothing physical is either infinite or infinitesimal in, say, the smooth motion of a projectile. And on the other hand, there's already an informal conception of what infinite does mean. It means bigger than anything merely big, or more of something than can be quantified even in principle, more of something than can be addressed in any sequence, however long. In that conception, the essence of finiteness is not about sets or mappings. It's about what computer theorists call effectiveness and what physicists call measurability or preparability, doability. And those two conceptions of infinity, the mathematical and the physical, draw the distinction between finite and infinite at completely different places. And that is essentially how Zeno of Elea, in his famous paradox, managed to conclude that Achilles will never overtake the tortoise if the tortoise has a head start, because by the time Achilles reaches the point where the tortoise is now, the tortoise will have moved on a little, and by the time he reaches that point, it will have moved on a little further, and so on ad infinitum. And thus, the catching up process requires Achilles to perform an infinite number of catching up steps, which, as a finite being, he presumably cannot do. Presumably. But do you see what Zeno did just there? He just presumed that a particular mathematical notion that happens to be called infinity faithfully captures the distinction between finite and infinite that's relevant to a particular situation in physics. And he was simply wrong. So he succeeded only in confusing himself, and there's nothing more to his paradox than that mistake. The truth is that what Achilles can or can't do cannot be deduced from mathematics or a priori in any way. It depends entirely on what the relevant laws of physics say. If they say that he'll overtake the tortoise in a given time, then he'll overtake it. If that happens to involve an infinite number of steps of the form go to where the tortoise is now, then he'll do an infinite number of such steps. If it involves his passing through an uncountable infinity of points in space, then that's what he does. But nothing physically infinite has happened. And by the way, what did happen didn't happen in steps. Okay, well, this distinction between finite and infinite is also at the heart of the theory of computation. For instance, an effective algorithm is defined as one that halts after a finite number of steps, where a step has to be defined according to a finite list of rules. And a rule has to be finitely executable, and so on. Now, these requirements were implemented in the classical theory of computation by, which was pioneered by Alan Turing, but they date back to mathematical requirements set by the mathematician David Hilbert in 1900 with the intention of formalizing the concept of mathematical proof. In fact, classical computations are essentially the same thing as proofs in Hilbert and Turing's sense, because every valid proof is a computation of the conclusion from the premises, and every correctly executed computation is a proof that the output is the result of the given operations on the input. Hilbert had required finiteness conditions. He had required that proofs use only a fixed and finite set of rules of inference, and executing a proof had to take only a finite number of elementary steps, and the steps themselves had to be finite. And so you recognize that from the theory of computation. That's exactly where finiteness, effectiveness came from in the theory of computation. Now, Hilbert contemptuously ridiculed the idea that his finiteness requirements were substantive ones. But do you see that he was thereby making exactly the same fundamental mistake as Zeno was? He was assuming that a particular mathematical distinction between finite and infinite in regard to steps and axioms and so on was self-evidently the one that corresponds to doable, effective, thinkable, and provable in physical objects such as the brains of mathematicians. Fortunately, Hilbert's intuition about finite and infinite, unlike the one that Zeno tried to implement, did match physics, as far as we know, even quantum physics. So his conceptual mistake didn't do all that much harm at first. And Turing's implementation of it was therefore enormously successful and fruitful. But the point is that if the laws of physics were in fact different from what we currently think they are, then so might be the set of mathematical truths that we would then be able to prove. And so might the operations that we'd be able to use to prove them with. The laws of physics that we know happen to afford a privileged position to such operations as and or and not, and to the concatenation of functions, and to individual bits of information. But if instead they were based on, say, Turing machines as elementary objects instead of points and so on, and if the laws of motion depended on functions like does this halt instead of on differential equations, then one could compute using operations which, with our physics, we call non-computable. While perhaps the functions that seem natural and elementary to us would be non-computable in that physics. Similarly, it's not just the distinction between computable and non-computable that depends on the laws of physics, but also the very important distinction between simple and complex. We now know, because of quantum computation, that Turing's and Hilbert's conception of what is simple and complex is not reflected in real physics. Quantum computation drives a coach and horses through the intuitive notion of a simple or elementary operation, and it makes some intuitively complex things simple. Okay, well, it might be objected that quantum computation, therefore, isn't real computation. It's just physics, just engineering. And it might be argued that the logical possibilities that I've just been describing about exotic laws of physics, which would enable exotic forms of computation, likewise don't address the issue of what a proof really is, or what a computation really is. So more precisely, the objection would go something like this. Okay, so under suitable laws of physics, we would be able to compute non-Turing computable functions, but that wouldn't be genuine computation. And similarly, we might be able to establish the truth or falsity of undecidable propositions, mathematical propositions. But again, that establishing wouldn't be the same as genuinely proving, because then our knowledge of whether the proposition was true or false would forever depend on our knowledge of what the laws of physics are. If we discovered one day that the real laws of physics are different, we might have to change our mind about the proof too, and its conclusion. And so it wouldn't really be a proof. So the objection runs. It wouldn't really be a proof, because real proof is independent of physics. Wrong. That objection is nonsense, because it would apply equally well to any proof. Our knowledge of whether a proposition is true or false always depends on knowledge about how physical objects behave, be they computers or just our own brains. If we changed our minds about what physically a computer or a brain has been doing, and in principle changing our minds could be due to changing our minds about what the laws of physics are, that they're not what we thought they were. For instance, if we decided that when formulae become sufficiently complex, computers or brains are subject to, there's a different term in the equations of motion that comes in and causes systematic false memories. This is a little bit like Roger Penrose's idea about what happens to the wave function when information becomes more complex than a certain amount. Then we'd be forced to change our opinion about whether we've proved something or not, whether something is proved or not, and possibly about whether we know it to be true or not. And here I must stress that whether a mathematical proposition is true or false is completely, that is indeed completely independent of physics. But proof is 100% physics. Proofs are not abstract. There is no such thing as abstractly proving something, just as there is no such thing as abstractly calculating or computing something. One can, of course, define a class of abstract entities and call them proofs, just like you can define a perpetual motion machine to be something else. One can define abstract entities and call them computations, but those proofs can't do the job of verifying mathematical statements if they're not effective or doable. A mathematical theory of proofs therefore has no bearing on which truths can or cannot be proved in reality or known in reality. And similarly, a theory of abstract computation as well has no bearing on what can or cannot be computed in reality. So, what is provable or unprovable is determined by the laws of physics in exactly the same sense as what the angles of a triangle add up to is determined by the laws of physics. Immanuel Kant thought that Euclidean geometry was self-evidently true. And that's another example of this same misconception that I've been talking about. The truth is that you can define abstract entities and call them triangles and have them obey Euclidean geometry. But if you do that, you can't then infer anything from that theory about, say, what angle you'll turn through if you walk around a closed path consisting of 3 straight lines. That thing might not be a triangle as you have defined it. Likewise, in probability theory, you can define abstract quantities that obey a certain calculus about mutually exclusive alternative events, and you can call those quantities probabilities. But in that case, your theory tells you nothing about how you should bet on real events. And of course, in quantum theory, real probabilities do not even obey those axioms of probability calculus that refer to alternative intermediate events. So, quite generally, things that happen in reality are governed by the laws of physics, period. And therefore, I can now give the definitive answer to the question that's the title of my talk and the title of the conference. What is a computation? A computation is a physical process in which physical objects like computers or slide rules or brains are used to discover or to demonstrate or to harness properties of abstract objects like numbers and equations. How can they do that? Because we use them only in situations where, to the best of our understanding, the laws of physics will cause physical variables like electric currents in computers representing bits faithfully to mimic the abstract entities that we're interested in. The reliability of the proof therefore depends on the accuracy with which those physical symbols do indeed mimic the abstract entities of interest. If we changed our mind about what the laws of physics are, we might indeed have to change our mind about whether a proposition we thought we'd proved was really true. Hence, the reliability of our knowledge of mathematics, nothing to do with whether propositions are true and false, just true or false, just our knowledge of mathematics, remains forever subsidiary to our knowledge of physical reality. Every mathematical proof depends absolutely for its validity on our being right about the rules that govern the behavior of some physical object, like computers or ink and paper or our brains. So, contrary to what Hilbert thought, contrary to what mathematicians since antiquity have believed and continue to believe to this day, proof theory can never be made into a branch of mathematics, nor is it helpful to think of it as a meta-mathematics, as it's sometimes known. Proof theory is a science. Specifically, it is computer science. So, that's what computers are. That's what computation is. That's what proofs are. Physical phenomena. That enables me now to turn to the subsidiary question: does nature compute, or how does nature compute? So, well, in one sense, yes, of course, computations are physical processes, and every physical process can be regarded as a computation if we just give abstract labels to all the input states and all the output states, and then just let the system evolve under the laws of physics. But precisely because you could always do that, no matter what the world was like, calling everything a computation doesn't in itself gain us any understanding of the world. But the world also has that amazing property that I referred to at the beginning. More broadly, it's computational universality. All those different computations embodied in physical processes are expressible in terms of a single finite set of elementary physical operations. They share a single uniform physical distinction between finite and infinite operations. And they can all be programmed to be performed on a single physical object, a universal computer, a universal quantum computer to be exact. And that's an object that can perform every computation that every other physically possible object can perform. And to the best of our knowledge, the laws of physics do have that property of computational universality. And it's because of that that physical objects like ourselves can understand other physical objects, i.e., to do science. And it's also because of that same universality that mathematicians, like Hilbert, can build up an intuition of proof and then mistakenly think that it's independent of physics. It's not independent of physics, it's just universal in the physics that governs our world. But in the class of all possible universes, that cosmologists nowadays postulate, not the many universes of quantum theory, but the cosmological ones with all different laws of physics. Most of them have other very different laws of physics to ours, and in most of those, there's no computational universality. In a tiny subclass, that's still infinite though, there is universality, but with all sorts of different computable functions. And also all sorts of different measures of what is simple and complex in those worlds. And all sorts of different criteria for what is finite and infinite in those worlds. And in some of those universes, there are analogues of David Hilbert or Alan Turing, each of them reaching towards a different conception of what counts as mathematically proving something, what counts as computing something. And I guess there are also lots of Stephen Wolframs, each of them seeking to base a new kind of physics on what they respectively experience as inherently simple self-evident computational foundations beneath his universe's contingent laws of physics. But in reality, there is no such distinction as simple versus complex or finite versus infinite, except as the laws of physics dictate. There is no mathematically preferred conception of computation or computability or finiteness or simplicity. Absolutely nothing other than physics and the cultural preferences that it conditions in us singles out Turing computable functions or cellular automata or even quantum computations or quantum cellular automata as being fundamental or special or elementary in any way. In fact, there's nothing that singles out the computation of functions at all, nor bits, logical variables, as being the fundamental forms of data on which computations operate. There's nothing deeper known about the physical world than the laws of physics. And I think there's nothing deeper known within physics than the quantum theory of computation. And for that reason, I entirely agree that it's likely to be fruitful to recast our conception of the world and of the laws of physics and physical processes in computational terms. And to connect fully with reality, it would have to be quantum computational terms. But computers have to be conceived as being inside the universe, subject to its laws, not somehow prior to the universe, generating its laws. The latter is the very misconception that led Zeno astray, and Hilbert, and Kant, and many other thinkers throughout history who haven't realized that while truth can be absolutely necessary and transcendent, all knowledge, even of such truths, is generated, computed by physical processes. And the scope and limitations of such knowledge are conditioned by nature's contingent laws. Thank you very much. I can hear. Hi.
Would you consider an experiment, a physical experiment in computation?
Yes. Yes. Sorry, I thought you were going to ask about a specific one. Yes, you can always regard any physical experiment as a computation. If the outcome is unknown, then it's a computation where we are probing what the computer is. And if the outcome is known, that is, if the laws are known, then doing is transforming the input into the output. Well, in order to make an experiment into a computation, you have to label, you have to give labels to all the input states and all the output states.
Let me have a follow-up question on that.
Yeah.
So suppose you perform an experiment, okay, and you figure out that nature tells you that the answer to your question, okay, your computation, takes basically a polynomial number of steps, okay? It's polynomially complex.
An experiment can't tell you that, because
you do the experiment and you can ask the question, how many, for example, how many resources you need to determine a very specific, physical property with a certain error. Okay?
You can only do that a finite number of times, so you can't tell if for large inputs it's polynomial or not.
Why you cannot?
Well, because in order to tell whether the resources are polynomial, you have to know how it behaves for arbitrarily large values of the input.
That's right.
And you can only ever do a finite number of experiments.
That's right. But suppose I can do that. And
yes.
Now my question is, now suppose that now with the well-known laws of nature, quantum physics, okay?
Yes.
I cannot find an algorithm, okay, that performs the same thing with the same complexity.
Yes.
What would you say about the laws of physics, nature, whatever? Would you conclude that quantum mechanics is not the right representation of, let's say, the way nature works, or what I'm missing?
Well, I'm not sure I understand what your proposed experiment is, but if you found that the idea is you guess, we conjecture what the laws of physics are, which tell us what we conjecture our computer will do. If we find that a real physical process can compute something, appears to be able to compute something in polynomial time that no algorithm can compute in polynomial time, then you would conclude that the laws that you thought were operating the device are not the true laws operating the device. So is that, if that's the question you were asking, then the answer is definitely yes. Yeah.
I don't want to, but yeah.
Okay.
Thank you.
Maybe the microphone?
Well, can you hear?
Is it your name or should I use the microphone?
Yes, I can hear, yes.
Okay, thank you. I completely agree that many mathematical concepts have a root in reality. And I also agree that some mathematicians forget it sometimes. Yet, it seems that there is an abstraction step that is needed to go from the root of the concept in reality to the concept itself. If we take a very simple concept, like the concept of natural number, of course it's rooted in the notion of cardinality, and the notion of cardinality is rooted in the notion of physical object. But if we restrict to the notion that is given by nature, we would reach hyper-finitist point of view where we say that there is a maximal natural number that has no successor.
Yes, and that would be silly.
In some sense, the construction of arithmetic is an abstraction step that frees us from this limitation that for some reason we do not want to consider. So in this respect, although it is rooted in reality, the concept of natural number is not in reality itself, but it's abstracted from reality.
Yes, well, it's not in physical reality at any rate. I mean, one could argue that there is that mathematical entities are real in a different sense, in that they have autonomous properties that we didn't necessarily put into them. But yes, so mathematical objects, that is why I keep stressing, I keep saying in my talk, that mathematical truth really is independent of physics. It's only knowledge of mathematics that is constrained by what the laws of physics say. So there's this enormous realm of mathematical truth which is independent of what the laws of physics are, and there's a window on that realm, a tiny window, which are the truths that we can know, and that window is determined by the laws of physics.
But when it's true of natural numbers, is true of proofs too. So, for instance, the notion of the mathematical notion of proof abstracts from when we see reality.
Yes. Well, yes. It goes like this. You can have physical intuitions about things, which are really intuitions about what the laws of nature are, and then you can abstract to make nicer mathematical quantities that don't have arbitrary restrictions on them. And then you can guess that those mathematical quantities are also instantiated in real physical objects. The class of mathematical truths that we can know about is much larger than the class that we can know. So, but there might be others that we can't even know about. Presumably there are, because the infinities involved are simply too large to allow knowing about them. Although I suppose we know about them in that sense. So yes, I mean, I think I agree. I mean, possibly you're making a subtle point that I haven't picked up, but yes, the proofs arise from a physical intuition. We then form a mathematical conception, a mathematical abstraction, which we call proofs, and then we conjecture that mathematical conception is actually generally true in physics. But we could be wrong about that last step. That mathematical object we have set up and called the proofs or laws of inference and so on, simply not correspond to reality. And if it doesn't, or it might only correspond approximately, and if it doesn't, then it's the set of things that we really can prove with physics that are the provable things, not the ones that mathematical conception might end up proving, because that is not effective in that case.
Okay, I think we agree on this one.
Okay, good.
I'd like to talk. I have one question about the computability.
Thank you.
So you said in the beginning that most or all computable functions, or all functions in physics are computable. And I wonder whether, and you said some proceed as a miracle or give some reasoning for that, but maybe it's just a very simple reason to explain that is that the laws of physics are usually expressed in terms of ordinary differential equations. And there's a theorem for these equations, that uniqueness and existence theorem. So in such a case, there will be always a solution to the equation, and only one, and you can actually say that if the laws are deterministic in this sense, it will always be computable. And if you look at the history of physics, physicists usually shy away from theories that were not deterministic. They already took determinism as heuristic. So maybe this is the reason why we express the laws of physics in such a way that they will be only deterministic, and this is why every function is computable.
Well, it's not a matter of arbitrary choice on the part of physicists. Physicists are trying to make laws that fit experiment, and it turns out that the laws, as we think they are, have this property. For instance, that they are differential equations, and not just any old differential equations, but well-posed differential equations, which have this property of computability. Now, I guess one can, this is a bit like anthropic principle reasoning. One can be amazed by this or not. I think I am amazed by it because in the bigger picture of mathematics, these things are very special. And we don't know of any mechanism or reason that why the actual laws of physics should be expressed in terms of those special kind of differential equations. And actually, even among that small set of differential equations, it's particularly simple ones that appear to be actually implemented. So we don't know why. Some cosmologists say it's an anthropic selection effect. We observers who can ask such questions only exist in universes where evolution happens, and evolution is a kind of computation that depends on the existence of simple computability. And I don't think that's a full argument myself. I mean, that would take us off on a tangent here, but I don't, although that may be true, it can't possibly be a sufficient reason for why the laws of physics are as they are, because the set of all possible laws of physics doesn't even have a measure on it, and so this reasoning about most of them do one thing and the rest do another it hasn't really got any basis. So anyway, yes.
I would like to. I like very much your position and your talk, but I would like to point out a possible similarity between mathematics and physics. You know, if you look at mathematics 200 years ago, most functions were continuous. And people believed that actually all functions are continuous. And then when they started understanding better, they had, you know, better tools, they discovered that most functions are not continuous. So maybe this is an accident, but that's just a, you know, a historical moment when physicists, you know, just look at laws which, you know, can be expressed by computable functions. And that's not something which is motivated by some good reason, but an historical fact.
Well, and now it can't be a purely historic effect, because the laws of physics as we currently believe they are extremely successful. They do, whether there might be corrections to them or there might be regimes in which they are completely wrong, but it is already a miracle that the laws of that the physical world is as computable as it already seems to be, even if in some other respects it may turn out to be non-computable or have discontinuous functions or not be governed by differential equations. It's already a miracle that it is as computable as it looks. So there is something odd there. It's not just that we've decided to look in one place. We've decided to look in one place and we found computability, and that's already a miracle.
Well, it's a miracle also that, for instance, in engineering, you know, if you look at, you know, buildings, bridges, planes, they all are built with continuous functions. You know, this is only in the imaginations of, you know, mathematicians, and discontinuities and all sorts of, you know, sophisticated deviations appear. So if you look at the pragmatic view, you know, one could say, well, from the point of view of engineering, only continuous functions count and exist.
Yes, but again, engineering has been successful at least up to a point. But prior to the scientific age, people tried all sorts of different kinds of explanations, sort of anthropocentric type explanations in which physical processes were governed by the intentions of supernatural beings and that kind of thing. And they were looking for explanations in those terms, and those explanations never were successful. So the fact that we can now build bridges using assumptions of continuous functions or something, even if it later turns out that that's just an approximation, that's already something that we don't know how to explain. Why are computable functions available to build bridges with? It's not just that we looked for them, we also found them.
Okay, another question. Yeah. I would like to a little bit more about explanation related to miraculously computable, and would this make our universe chosen among all alternatives just because those are more computable, and of course the connection is evolution being more likely this study?
Well, as I said, I don't think that can be the full explanation of this mystery. It could be that there are all sorts of universes with different laws of physics, and it could be that in most of them, in some sense, there are no observers. However, there has to be a structure on this class of universes such that most of them make sense. If you take just the set of all possible laws, which is not a set but a class, it's too enormous for the concept of most of them do one thing while a few of them do another to make sense. So you can't get out of this problem purely with anthropic reasoning. That the answer must be some kind of explanation of why the laws are as they are, or at least why the measure on all possible laws is as it is. That kind of thing. So I think if you're asking, is anthropic reasoning enough to explain this? I think not.
Well, the interesting situation with computability is that obviously computable functions are measured at zero, and all alternative universe
Yes.
in favor of the choice of universe very unlikely.
Yes, quite so. Quite so. So there's something to explain. It's not just selection.
I guess we can only take one more question. So how many questions do we have? Well, let me just take it from a person who never asked any question yet. You, yeah.
Hi, in your position that proofs are things that are computable in physical reality, and mathematical proofs are what it is. I was interested in how does this relate to the difference between classical proof and constructive proof, as in using classical logic and constructive logic?
Okay. Well, I'm not an expert on that, but I think I can tell you what the situation basically is. Proof theory, like I said, proof theory is a science. And one of the changes that one has to make already, never mind these exotic laws of physics that might exist, the change that you already have to make with quantum computation is that we can no longer define a proof as an object that is. Traditionally, we've thought of a proof as being something you can present on a piece of paper that satisfies certain laws. Like at the beginning, there must be axioms, and then it proceeds in lines, and then each line must follow from the axioms according to a set of rules of inference. And then the last line is the conclusion. Then we say the conclusion is proved from the axioms. Now, in quantum theory, that is no longer sufficient. There are other kinds of proof that cannot be expressed in that way, at least not in a tractable number, not in a polynomial number of steps. There are proofs where there is not enough paper in the universe to express them in that way, but a quantum computer could nevertheless prove them. And for that reason, you have to change your... In classical physics and in classical theory of computation, the idea of a proof as an object obeying certain rules and the idea of a proof as a process where you do one of the lines after the other, where you execute one operation after another, are equivalent. There's just a 1-1 correspondence between those two conceptions. But in quantum computation, there isn't a 1-1 correspondence, and it's possible that some things that can be done in a small number of simple steps can't be expressed except in an exponentially large object. So those distinctions between different kinds of proofs are induced by the laws of physics, and if the laws of physics are different, the classification of proofs will be different as well.
Unfortunately, I think we'll have to finish here, so let's thank
having me. Nice meeting you.
Thank you very much.
Bye-bye.